Welcome to another video. In this problem, we are asked to find the homogeneous solution to these differential equations. Now, these differential equations look very similar to the constant coefficient differential equations. However, you'll notice that they have some functions of t in front of the derivatives. And when the powers of t decrease with the order of the differential equation, you have what is called the Cauchy-Euler differential equation. So these are all Cauchy-Euler differential equations. And the typical form of a Cauchy-Euler differential equation looks like this. And in this case, these are all homogeneous. And you'll notice that if you were to remove the t squared and the t, this is exactly constant coefficient. And it turns out that they're very similar to constant coefficients. But with Cauchy-Euler differential equation, you don't make the guess e to the rt, you make the guess t to the r. And the reason for that is when you take the first and second derivative, so y double prime would be r times r minus 1 t to the r minus 2, and when you plug them in for y double prime, y prime, and y, every single term will end up having a t to the r in it. You can factor it out and cancel, and you are left with what is called the characteristic equation, which looks very similar to the auxiliary equation. It is ar squared plus b minus ar plus c equals 0. So again, this is very similar to the constant coefficient case, but now we are dealing with what is called a Cauchy-Euler differential equation. We still have the three different cases that it can fall into, which is um, real and repeated roots, real and distinct roots, and complex conjugate roots. So let's dive in and see which each one of these problems gives us. So in part A, the A value is the coefficient in front of the t squared y double prime, which is 1. The B value is 1, and the B value is negative 1, and the C value is positive 1, which gives us the equation A, which is 1 r squared, plus b minus a, so negative 1 minus 1r, plus c, which is 1, is equal to 0. This is r squared minus 2r plus 1 equals 0, and this equation factors nicely. It factors as r minus 1 times r minus 1, giving us our two roots of 1 and 1. So we are in the real and repeated root case. So our two solutions are, remember, you are plugging in these r values here in t to the r, so it's t to the first and t to the first. The problem, however, is that these are not linearly independent. So just like in the constant coefficient case, we have to multiply by something else to make the second solution linearly independent. And in this case, when we're dealing with Cauchy-Euler, you always multiply by the natural log of t. Okay, so in the constant coefficient case, you multiply by an extra power of t. In the Cauchy-Euler case, you multiply by a natural log of t. And that gives us the homogeneous solution, c1 t to the first plus c2 t to the first natural log of t, as our homogeneous solution to part A. So part B, up here, notice the A value is equal to 1, the B value is negative 2, and the C value is negative 4. So what we have here is r squared plus b minus a r plus c equals 0. There's our characteristic equation. And this simplifies. Let's see, r squared minus 3r minus 4 equals 0. This factors nicely, r minus 4, r plus 1. So our two roots are 4 and negative 1. So our two linearly independent solutions are t to the fourth and t to the minus first, which we're in the distinct case. These two solutions are linearly independent. So our solution is c1 t to the fourth plus c2 t to the minus first. Okay, so part A gave us the real and repeated roots case. Part B gave us the real and distinct roots case, which, you know what, probably means that part C is going to end up giving us the complex conjugate case. Let's see if that's indeed the case. So let's rewrite this equation down here. So 4t squared y double prime plus 17y equals 0. And we also have some initial conditions. I'm not going to write these down just yet, but these initial conditions here are going to allow us to find what the values of the constants are in the homogeneous solution. So we'll come back to those once we have our homogeneous solution. So this is again Cauchy-Euler, and also note that there is no b value here. There is no y prime term, which means that b is equal to 0 when we are creating our characteristic equation. So it is 4r squared plus b minus ar plus c is equal to 0. There's the characteristic equation, and we can take it one step further. So minus 4r plus 17 equals 0. That, I don't think, factors nicely. 4 times 17, that is 68. Two numbers that multiply to be 68 and add to be negative 4. We're not going to be able to find them. So let's go ahead and use the quadratic formula. So we are now using these values for negative 4 and 17 as the a, b, and c values in your normal quadratic formula. So opposite b plus or minus the square root of negative 4 squared, which is 16, minus 4 times a times c all over 2a. All right, so this is 4 plus or minus the square root of 16. Okay, 16 times, I don't know what 16 times 17 is off the top of my head, but both of these terms, if I just write the 4 times 4 as 16, I can actually factor out a 16 from both of these pieces, which gives us, let's see, 4 plus or minus the square root of 16 times 1 minus 17. Ah, this is nice. So 4 plus or minus the square root of negative 16 times 16, all over 8. So indeed, we are in the complex conjugate case because of the negative here in the square root. So we'll bring that out to be an I. And the square root of 16 times 16 is just 16. So our two roots are 4/8 plus or minus 16 over 8, which is 2i, or 1/2 plus or minus 2i. All right, now in the complex conjugate case, you should identify what the alpha and the beta are in terms of your roots. And in the complex conjugate case, when you're dealing with Cauchy-Euler, the two solutions are, remember, it's not e to the rt. I'll remind you, our guess was t to the r. So you take t to the alpha power times the cosine of beta natural log of t. And then your second solution is t to the 1/2 sine of beta natural log of t. Okay, so our homogeneous solution just puts constants in front of these and adds them together. So c1 t to the 1/2 cosine of 2 natural log of t plus c2 t to the 1/2 sine of 2 natural log of t. And now we need to remember that we were given some initial conditions. So we were given that y of 1 is negative 1 and y prime of 1 is 0. So y of 1 is negative 1 and y prime of 1 is 0. These two initial conditions will allow us to find what the values of C1 and C2 happen to be. Now, what we're going to be doing here is we're going to be plugging in 1 for t. So here and here and here and here, because we'll use this condition first. And I'll remind you that the natural log of 1 is equal to 0. Okay, so the natural log of 1 is equal to 0. Also, when the natural log of 1 is equal to 0, that means that what's inside of the sine and cosine will be 0. So we need to know what the cosine of 0 and the sine of 0 are in this case, which the cosine of 0 we should know to be 1, and the sine of 0 we should know to be 0. Okay, so now if we plug in this initial condition, we get negative 1 on the left is equal to C1 times, well, this will be 1, times this will be 1, plus C2 times, well, this will be 1, times, well, this will be 0. There we go. And C2 will be multiplied by 0, which means this whole term is gone. So we just get C1 as negative 1. All right, so we're halfway there. So our homogeneous solution, I'm going to rewrite the homogeneous solution with this negative 1 plugged in here, gives us negative 1 t to the 1/2 cosine of 2 natural log of t plus C2 t to the 1/2 sine of 2 natural log of t. All right, now we need to use this second condition, the derivative condition, and that will allow us to find what this C2 is. But in order to use the second condition, we need to find the derivative. And let's see here. Well, the way it's written in this form, we would need to do two different product rules to find the derivative. One product rule here and then another product rule here. We can avoid that if we factor out a t to the 1/2 from both of these. And we'll be left with negative cosine of 2 natural log of t plus C2 sine of 2 natural log of t. And the only reason we might do this is it makes our derivative a little bit simpler. Now we only have to do one product rule. Okay, so now let's buckle up. Here we go. The derivative, well, we find the derivative of t to the 1/2, which is 1/2 t to the minus 1/2. We will leave the other piece alone, so it's the same negative cosine natural log of t plus C2 sine of 2 natural log of t plus, now we need to do it the other way around. Now we leave the t to the 1/2 alone, and we find the derivative of this inside part. Well, the derivative of negative cosine is sine, so positive sine. Leave the same inside function. And then the chain rule says to multiply by the derivative of 2 natural log of t, which is 2 over t. And then we'll do the similar type of thing to find the derivative of, I should say, it's this piece, which will give us C2 times the derivative of sine, which is cosine, 2 natural log of t, times, again, the chain rule allows us to put forces us to put a 2 over t at the very end. So there's our derivative. And we need to use this condition, y prime of 1 is equal to 0. So y prime of 1 is equal to 0. When we plug in 1 for t, it will go here, which will make this natural log of 1, which is a 0. So this whole thing will be 0. And the cosine of 0 is 1. So this whole thing, this whole piece right here is going to be negative 1. Similarly, this whole piece here is going to be positive 1. And remember that the sine of 0 is 0. So when we plug in 0 here, let me highlight this here, which will cause this natural log of 1 to be 0, which will cause this to be the sine of 0, which the whole thing is 0. So this term is gone, and so is this one for the exact same reason. And that 2 over t goes with it. Okay, what else? What else happens? Well, notice that this will be 1 to a power, this will be 1 to a power, so those will both be 1. And this here will be a 2. So I think we're in good shape to now just plug in the value. The derivative is 0. And what do we have here? We have 1/2 times 1, that's this piece, times negative 1 coming from the cosine, plus 0, that's the sign, plus, now we're looking at this part here. Well, the t to the 1/2 in the front is just a 1, and in the parentheses, this is 0, plus c2 times 1 times 2 over 1, which is just 2. So we need to solve for c2 here. We get 0 is equal to negative 1/2, that's all of this, and this will be plus c2 times 2. Or positive 1/2 is equal to 2c2 after I move this to this side, and therefore c2 is equal to 1/4. And there we have it. There is our second constant, which gives us our final unique homogeneous solution by plugging in the c2 value here, which is 1/4. So we have this, so that's negative 1 times t times, I forget, was that the cosine? Yep, the cosine of 2 natural log of t plus 1/4 t, whoops, I forgot the 1/2 over here, t to the 1/2 sine of 2 natural log of t. Let me double check that. Does everything look right? Yes, everything looks good. Here is our unique solution to that Cauchy-Euler initial value problem. So in this case, we dealt with both or all of the real and repeated roots case, real and distinct root case, as well as the complex conjugate root case. I hope this video helped someone. Good luck on your exams.